All right, so we're claiming that we've made a simple technical solution to the adiabatic engine, or I should say to the lubrication problem, the perpetual lubrication problem faced by adiabatic engine designers, most notably the 700 degrees Celsius cylinder wall temperature, which basically vaporizes any mineral lubricant known to man. This is arguably an insurmountable problem because you're fundamentally dealing with chemistry and the hydrogen bonds and carbon bonds in the actual oil, the molecular structure of the oil. So you can't really engineer or innovate your way out of that. So an adiabatic engine has to be free of lubrication. Now you could use dry lubricants. You could use molybdenum disulfide or tungsten disulfide, but they don't really confer that hydrodynamic type of boundary layer lubrication that you get with a mineral oil. It doesn't produce a film. It's just a powder. It's a heterogeneous powder. So what we proposed is we got an inspiration from a paper that was written by some guys that worked on the TACOM program by Cummins, which investigated the adiabatic concept for tank engines, for military truck engines, because a radiator turns out it produces a great deal of vulnerability for vehicles operating in these kinds of very, very harsh regimes where you might have very high temperatures. And if your coolant system fails, the vehicle's inoperable. It's rendered inoperable. So, if a bullet pierces the radiator, you're finished. Anybody who's ever had problems with their radiator, their coolant system, can attest to this. So the rationale behind the TACOM program was not just to boost the BCFC, because it already was. I mean, they were able to achieve simply record-breaking efficiency, because obviously you're not dumping out 25% of the energy as you are in a conventional oil water-cooled engine. I mean, if you think about it, it's rather asinine that you're dumping about 25% of the energy out basically into the air. You're pumping it into the radiator and it's carried out by the air that blows across the vehicle. So you're basically throwing money out the window, and you're reducing your range and increasing your operating costs. So preserving that heat and turning that heat into gas expansion makes a lot of sense. But if you want to do that, it's also the logical conclusion of the internal combustion engine, right? It's far from obsolete, right? If everybody says, "Oh, it's obsolete," then certainly it's not. So there'll be internal combustion engines on Earth in 1,000 years. But the logical conclusion is turbo compounding, where you maximize the recovery of kinetic energy from the exhaust gases, and an adiabatic system where you internalize all that heat, you retain, you bottle up all that heat and force it to do useful work. So it turns out that if you do that with turbo compounding, you can probably get about 55% efficiency on a small diesel engine. And that's simply unparalleled by any other thermal power plant we know of. Even an electrochemical power plant like a PEM fuel cell or polymer exchange membrane or proton exchange membrane, they're barely like, from what I've seen, I looked at some Chinese fuel cells, they're like 52% for PEM, and by the time you go through your inverter, a rectifier, and go through an electric motor at the wheel, you have to have a gearbox then, right? You're probably like, sort of mid-40s efficiency, so you're not really much better than your typical common rail diesel engine from Volkswagen or whatever. So the adiabatic engine is at the efficiency level of a large Wärtsilä 100,000 horsepower marine diesel engine that burns bunker fuel. We're talking like 0.225 pounds per horsepower hour or below. That's a record-breaking efficiency. So if you could sell an adiabatic engine to trucking fleets, and then you design it to run on hydrogen, you're basically dealing sort of the ideal technological solution. Of course, when I say hydrogen, I would mean that hydrogen would be supplied by ammonia that would be reformed on board. I don't believe in storing hydrogen at high pressure or anything like that. But returning to the basic mechanics or kinetics of the engine, you need to do two things, right? You need to eliminate the mineral lubricant. So therefore, you have to either do two things. You have to just accept a high wear rate in a dry lubricated engine where you have ceramics rubbing against each other. And you can do this. I mean, there are ceramics that have relatively high oxidation resistance, have very low wear rate coefficients that you could use. And remember, there isn't force against the piston ring. I mean, it's sort of just barely sliding against it. It's not like a traction drive or something where you have a lot of force and friction, right? I mean, or I should say friction is a function of force. But like a train, The reason there's a lot of wear is because there's a weight of the train grinding down. If you have a grinding wheel, you put a knife against it, there isn't a lot of wear unless you put pressure on the knife. So you have to actually push against the grinding wheel with the knife. So if you have a typical piston ring, isn't really being pressed against the cylinder wall. There's not really much force on it. So you could have a dry lubrication system with just ceramic. That could absolutely work. The math works if you look at a wear rate coefficient. Now, of course, those are at room temperature. The numbers that I've looked at, the wear rate coefficient tends to increase with temperature, and of course, at in an oxidating environment, you would also have oxidation. So a better solution is not to rub the ceramic ring and liner against itself. Rather, you would have an air lubrication system or a gas lubrication system where, rather than a lubrication system, it's actually more of a seal, where you would actually route high pressure gas at above the background cylinder pressure through little passageways in the piston. You have you have a crosshead, right? So you have an intermediate shaft or pipe that sticks out basically beneath the piston that is supported, rigidly supported in a housing that reciprocates vertically. It doesn't allow transverse or any lateral movement, and that would be conventionally hydrodynamically lubricated with a mineral oil. But that's isolated from the hot combustion gases, so that's not going to burn up the lubricant. And then, where you actually have your combustion zone, you have this piston that's firmly or rigidly attached to the to that housing, and that way, because on a conventional engine, you have this transverse and lateral motion, and the piston is getting slammed back and forth against the wall. So you do have force actually rubbing against the cylinder wall. So that's actually a very stupid design. A free piston engine, for example, doesn't have that. Free piston engines have considerably lower wear. They have better turbological performance. So for an adiabatic engine, we cannot allow any physical contact between the ring and the wall, and so as a consequence, we have to firmly, rigidly fasten that cylinder so we can only reciprocate. And we can do that. I mean, manufacturing tolerances today are much higher, and if we use ceramics, the thermal expansion coefficient of ceramic is considerably lower than metal, and so you could achieve higher tolerances. But then, of course, you don't want gas to be blasting past this gap, because if you don't want to, again, rub the ceramics against each other, you would have a gap. And so you would use air to seal that, so that you would introduce high pressure air underneath to blow past that ring gap, so that the hot combustion gases would be forced to stay inside of the chamber, because the gas would be at a higher pressure than the combustion pressure. The pressure of combustion isn't very great outside of the first few milliseconds or milliseconds, I guess. Peak firing pressure. So the BMEP is a tiny, well, not a tiny fraction, but considerably less than the peak firing pressure. Maybe your peak firing pressure is 250 bar, and your BMP is 35, 40 bar, something in that range. So, but yeah, the basic idea is to firmly root the piston in something like a crosshead, like on a marine engine. Marine engines have this intermediate shaft that sticks out between the actual piston skirt, where you would otherwise mount the piston to the top of the connecting rod. It's actually mounting to the end of this intermediate shaft, and then the other end of the intermediate shaft connects to the bushing where you would connect your connecting rod. So that way you don't have that lateral force whacking the piston back and forth inside of the cylinder wall, and of course that produces wear, and that's unacceptable because we don't have the ability to lubricate this thing. So really, all we want to do is prevent a lot of gas leakage, and we can easily do that by simply, again, pressurizing the piston. So, or pressurizing the piston ring area where you have the gap. So that's about it. And as far as introducing the gas, you can very easily do that, because again, when you have the crosshead, they have the oil quills on the marine engines. They'll actually spray oil circumferentially on these little oil injectors to keep the liner nice and lubed up. But we wouldn't be using any lubricant, so we wouldn't have the particulate emissions, the carbon monoxide, the NOx that's produced from burning oil. So we'd be a full zero-emission engine because we run on hydrogen, and that means it qualifies as a zero-emission engine, unlike the conventional hydrogen ice, which still burn the lube oil. So we have no lube oil. And of course, if you think about a hydrogen internal combustion engine, well, if anybody knows anything about those engines, they'll know that the biggest problem was NOx and lean burn, because your three-way catalytic converter, palladium, platinum, rhodium catalyst goes from basically 100% efficacy of converting NOx into nitrogen oxygen to 50% or less if you run it just a little bit over stoichiometric. In fact, you want to run it a little bit rich for ideal conversion efficiency. So, in fact, hydrogen actually aids the conversion of nitrogen oxides into nitrogen. So, but of course, if we remember what MAN did, MAN tried to run their hydrogen ice stoichiometric, port fuel injected. And of course, you do that, you have issues with backfire and preignition because the hydrogen's. If you did this on a adiabatic engine, it would literally ignite right away because the cylinder wall temperature would exceed the auto ignition temperature of hydrogen. Right. So you would direct inject the hydrogen. You would preheat the intake air so it would ignite upon injection, just like a conventional diesel cycle. And you would effectively have the efficiency of the diesel cycle, but with the emissions of a fuel cell or something like that. And of course, in your dual fuel, you don't have to run just hydrogen. You could run any other kind of fuel. You don't limit your power plant to one fuel, which reduces the value of the vehicle. It makes it less versatile. And so that's basically the situation. Hydrogen internal combustion engines are potentially very effective. About the only solution we know of to replace conventional liquid distillate hydrocarbons. And again, we should emphasize we're doing this not to reduce CO2 emissions, because that's not a problem. There's no issue with CO2 emissions. The issue is twofold. The principal issue is that anytime you run an engine with a rather viscous fuel that has a carbon-carbon bond, you will produce solid carbon particles, nanometer-sized particles, PM10, PM2.5, abbreviated cylinder carbon black, or carbon black is the technical term actually. And it's very, very difficult to filter this out. You can use your Coderite or silicate monoliths, aka a DPF filter, but those have to be replaced quite often. When you open those things up, it's extremely dangerous to breathe that fine stuff in. And of course, then it's very difficult to after treat a diesel engine because they're so lean. You can't use your TWC. You have to use SCR, and urea injection is not very effective. And so getting a diesel engine to be clean, I mean, you can do it, and they have done it. It's very, very effective, but it imposes a considerable burden on the operator. Additional maintenance costs, reduced performance because you're adding all this back pressure, because there's pressure drop across these monoliths. So if you have a internal combustion engine that runs on hydrogen, that could be a diesel cycle, you'd have the torque, the performance, the low cost, the flexibility, the power density of the diesel powertrain, but basically the emissions, your emissions would simply be water vapor, right? And so that you almost sounds too good to be true. I suppose it is, right? Because every good invention is too good to be true, right? The diesel engine was literally, when Rudolf Diesel built that thing, it was 35% more efficient, 40% more efficient than your auto cycle, and it lasted longer. You couldn't really get better than that. But people are all, it's really a blessing in disguise for me, because people are so enamored by silly ideas like batteries and fuel cells that they don't spend any time on this. And so pretty much the only one that's working on this, as far as I know, in the world.